Welcome back to ECE 320A. Wow, last class -1, is that true? We just have 2 more lectures, including this one. So if you're counting down the days, you've almost finished the countdown. We have 1 more day to count down. And because of that celebration or that high anticipation, we're going to make a homework due on each of those. Actually, a little bit different. Homework 9 is due today, and I can see that everyone has completed that nicely. So that can be turned in at class or after class. But homework number 10 is actually due a day beyond the next time we meet, if that's agreeable to you. If you want to, you can hand it in on Tuesday, the next time we meet, which is the 1st of May. And that's by 4 o'clock in my mailbox, or it could be, depending on what we decide, and this will be an in-class participation today, can you vote for which time you would like me to start the review session? 4 to sometime or 5 to sometime, and it will be held on Wednesday, the last day of class, so we won't see each other that day unless you come into office hours on Wednesday morning. But your homework will be due that day, and if you do turn it in at the ultimate hour, please have it available when we start that review session. If the review session starts at 4, you won't have to try to find my mailbox. You can just bring it to me. I will try to put all of this information up on D2L because there's quite a bit yet to follow, and I just want to make sure that the key is that the final exam is on Tuesday the 8th of May from 10:30 to 12:30. Definitely make sure you know that. That's the final exam for this, and vote for your favorite start time on that Wednesday. I apologize, but every day is really full up until that last afternoon. So if you can't make it, I will try to record that and make that available through D2L, that particular review session. I have tallied the votes on what you wanted to see reviewed, and three-phase power was just standing out tremendously from the others, but Bode plots was close, as was convolution. So I guess I'm not surprised at that ranking of topics. I do not want you to think that you don't have an opportunity to ask some last-minute questions before the final. Here are the office hours that I'm proposing that will occur before the final exam. Wednesday and Thursday of next week. Thursday is reading day. You hopefully won't have any classes to attend on that Thursday, but I will go ahead and have my normal office hours from 9 a.m. to 11. So you shouldn't have a conflict with that, but maybe you still do. Friday, the following day, will be from 2 to 4. So if you want to have some questions answered before you go into your long weekend of studying for this class, hopefully we can get some of those little tweaks done so that your studying is even more effective. If you do have questions after the weekend of studying before the final exam, I will have 4 hours on that Monday, the 7th, from 9 to 11 and from 3 to 5. And when was our final exam? The following day on Tuesday at 10:30 a.m. Make sure your alarm, if it's on a weekly schedule, is maybe adjusted so that you get to this class at 10:30 instead of 12:30. So it's 10:30 a.m. to 12:30 p.m. on the 8th of May. And that's a Tuesday. Questions on the process. So you have a difficult in-class participation question to answer, and that is, when would you prefer to have that start, the review session, 4 or 5 o'clock on Wednesday, the 2nd of May? And if you are unavailable, you can answer that way. You can say, I'm unavailable, and so you don't want to influence the vote. You can abstain, but still turn in your paper. You can say unavailable, and that will still get you credit for your in-class participation. I'm sorry? You could vote for both, I guess, yes. This is not an exclusive or ballot. Yes, you could vote for both hours. Today I have a long list. We have to now put half of the semester's content into 2 lectures. No, not really. What I want to be able to cover, and I'm not sure how extensively we will cover it, but we will try to get into 2-port circuits or 2-port networks. Today we will probably only get this far, and that is to finish up our low-pass filter example that we started last time, and that was to introduce frequency scaling and magnitude scaling on a very simple filter. It was a low-pass first-order filter. We will look in general at what happens, or the strategy involved with scaling polynomials. If somebody gives you a 6th-order Butterworth polynomial and they say, I want the cutoff frequency to be 2067 hertz, you can figure out how to scale that from the formula that's provided, or the polynomial, the normalized polynomial that is given in table 15.1. And the normalized polynomial has a cutoff frequency or a bandwidth of 1 radian per second. We'll talk about that via an example. Then if we're talking about Butterworth polynomials, we better start talking about the filters that you can implement with those, or how do you now create filters that have these characteristic roots, or those pole locations. So we'll talk about Butterworth filters. We'll introduce that by looking at the basic, or let's say the fundamental 2nd-order section. You already know how to create a 1st-order section or factor of a op-amp circuit, and this way, if you have a 2nd order, now you can build any order or filter you want. You simply put these pieces together. If you want a 5th-order filter, you take a 2nd-order section, cascade it with another 2nd-order section, and cascade that with a 1st-order section, and now you have a 5th-order filter. And we'll learn how to adjust the poles of those 2nd-order sections in this discussion. Then we will simply provide the formula for approximating what order do you need if somebody has a particular specification on their low-pass filter. They say, oh, I need it to be 20 dB down by a given frequency. We'll see what that implies as far as the order of the filter. The higher the order of the filter, the faster the roll-off. The more steep the magnitude is falling off as frequency increases. Then we'll look at some design steps for actually building some Butterworth filters. We will design a 3rd-order Butterworth low pass by means of an example, and as I said, if we have time, we'll get into 2-port circuits, which is another chapter of the book. Let's start with our example from last time. In that example, we wanted to design a low-pass filter. We wanted that low-pass filter to have a bandwidth of 100 hertz. And again, you have to keep track of whether you're talking hertz or radians per second in the frequency specs. We wanted a gain, and there maybe I wasn't very clear or specific. We want the passband gain to be 2. And what does that mean for a low-pass filter? So we now want the DC gain to be 2, and we're assuming now that that's fairly flat, and it will actually be 3 dB down at the break frequency or the cutoff frequency. And that's our half power point. So it's rolled off a fair amount even by the cutoff frequency. And we bought a gross of capacitors, and they were 1 microfarad. We got a good price on those, so we want to make sure that our filter uses at least one of those 144 capacitors that we purchased. That making sense? So we want to fix our design such that we use a 1 microfarad capacitor. If you had another capacitor value that you had in your stock or supply, you could use that other capacitor. You could magnitude scale your results to get the appropriate expression for capacitance. Here's figure 15.1. That's the generic first order low pass filter section. That will give you a 1 in terms of your order. So if you have an odd order filter, you would hang this on to all of your even or second order sections in your design process. Hanging meaning you simply are cascading these all together. And that's the beauty of working with op amps, is they allow for this nice unloaded behavior of connecting sections from one to the other to the other to the other. They can sort of be designed individually and then put together. That's what we're playing on or living with. There is our circuit. Last time, and if you don't remember, you should be able to rederive that transfer function. That's a first order system. It has nothing in the numerator. Its DC gain is R2 over R1, and it has a time constant of R sub 2C. And from the time constant, you could actually get the pole location, which is at minus 1 over R2C. It's where that denominator vanishes. To simplify things, we said, oh, well, if we just set all of those parameters to 1, we would get a fairly nice looking transfer function. And this we could say is our normalized transfer function, 1 over S plus 1. And this then first order section has a cutoff frequency of 1 radian per second with with both R's and your C set equal to 1 ohm or 1 farad in value. That's typically not going to cut it. We're going to have to modify those R's and C's to shift that frequency to the location that we want it. So that's just some facts relative to that particular transfer function. It has a bandwidth or a cutoff frequency of 1 radian per second. It has a DC gain of 1. Our design, we wanted our cutoff frequency to be 100, but that was 100 hertz. So I'll call that F desired. And remember, as long as you're still gainful or even forever, you should remember omega is equal to 2 pi f. Okay? Even in retirement, you should remember omega is equal to 2 pi f. With that f, we now have our new omega, and that's what we want to design these filters in terms of, is a radians per second, is 200 pi. Our frequency scaling expression that we had agreed to use was our new frequency, omega sub 2, is equal to k sub f, a frequency scaling factor, times the old frequency, or omega sub 1, the starting frequency. Solving that for k sub f, this number that we want to plug into our formula, scaling formula, is now omega new over omega old, or 628.3 radians per second. That's k sub f. We also had a design constraint that we wanted to use a 1 microfarad capacitor. And what that really is saying is we want to use our magnitude scaling factor, K sub m, to fix our capacitor at 1 microfarad. And we knew from our magnitude scaling formula that the new capacitor value, and this we derived last time, I believe, the new capacitor, C sub 2, needs to be equal to the old capacitor, C1, divided by both scaling factors, K sub m and K sub f. We've already, our original circuit had C1. Our new circuit is C new, and we want that to be 1 microfarad. We have our we have our frequency scaling K sub f, and we now need to find our K sub m. So here's K sub m that we would like to have, and the only thing now that's left in this design to find a 100 hertz cutoff frequency is to scale our resistors. We know that we're using a 1 microfarad capacitor. That's how we found this magnitude scaling number. So now we can say, okay, the new resistors, and maybe so R sub 1 new is going to be K sub m times R sub 1 old. And the old capacitor we had set equal to 1. And now we try to find the resistor value closest to 1591.6 in the bin of resistor parts. Likewise, we had one more resistor. And because it started with the same value, we should end with the same value with these scaling parameters K sub m. And the resistors are not a function of frequency, so those don't have to change with K sub f. Now, if we went back to our design specs, we have now already designed a 100 hertz bandwidth. We've used our 10 microfarad capacitor. What we haven't talked about is the gain of the circuit. What's the gain right now in our circuit? We haven't changed that gain, have we, from the original design? And that original design had a DC gain of 1, and we haven't changed that by scaling in frequency or in magnitude. We haven't changed that net gain. Now what we want to do is really go back to our original expression for the transfer function, which is right there, and say, oh, how do we adjust the gain? So now we can mess with this ratio R2 over R1, can't we? That's what's impacting our gain. So we can play with R2 and or R1, but the key thing to keep in mind is if we do mess with R2, it's going to change our time constant, which is going to change the cutoff frequency. So we really probably don't want to be messing with R sub 2 unless we want to keep going iteratively through this to change everything that will be impacted by changing R sub 2. Is everyone clear on that? If we want to just adjust the gain without changing the frequency or the break, we probably should leave R sub 2 alone, and then that will reduce our workload. So we have a gain of 1. We can adjust R1 and or R sub 2 to actually modify the gain. But I hope that transfer function, going back and looking at that, made us realize that if we do change r sub 2, that also influences the cutoff frequency. And because of that, let's go ahead and just adjust the gain by changing r sub 1. And for that, we simply need R2 over R1 to equal 2, or R1 is now going to be R sub 2 in half, or cutting R sub 2 in half, meaning that now the R sub 1 or the R sub 2 that we have found after the initial scaling was this 1591.6. We cut that in half and we end up now with an R1 value of 796, roughly. Questions on that design? We've now designed a first-order low-pass filter with a cutoff frequency of 100, and you should be able to see that magnitude and phase. Since it's not that complicated at this point, you should be able to sketch that in no time if I ask you to sketch that on an exam, or if I ask you to sketch that on a napkin, if we were just having a discussion about low-pass filters. Questions on that example? Let's talk then about frequency scaling in sort of general. Or what if somebody gives you a particular polynomial and they say, oh, here's s squared plus 0.765 s plus 1 times s squared plus 1.848 s plus 1. If somebody said, what's the natural frequency of those two factors? Is the natural frequency the same on those two factors? The first question might be, what's the order of that polynomial? It's fourth order. So you have 4 roots of that polynomial, and if you put that in the denominator of a transfer function, that would now have 4 poles associated with it. You now have a fourth order polynomial. Is that transfer function stable? Can you make that call? The answer is yes, you can make that call. It is stable, and the reason is because you have 2 second orders. It's already factored into the second order, and each one is present and positive, meaning this constant coefficient is present, it's positive. This first order coefficient, or the coefficient multiplying s, is present and positive. Likewise, this is present and positive, and this is present and positive. Both second orders are stable. They're in the left half plane. The combination of those is stable. This is a stable polynomial if it's associated with poles. And now we've answered a couple of questions. What is the natural frequency? Where would those poles be located? Or the natural frequency really tells us how far away they are from the origin. If you looked at Butterworth poles, this is, now I'm ad-libbing, but if you simply looked at a first order polynomial that was normalized, it would have a pole right there at -1. If you now looked at a polynomial, and maybe I should This is getting scary when I start ad-libbing. But now we have, if we had, well, another way of thinking of this, a lot of times when people are talking about Butterworth poles, they say, oh, take all of the poles, if you use that pole location to find a radius, then that pole would be on this circle, and this is the complex S-plane. That circle would have a radius of 1. And typically when people, that's not a very clean circle, but you can get your protract or your compass out and draw that circle more accurately. When people are talking about Butterworth, really what you want to do is start splitting the unit circle up into equal pieces or sections. So if you're thinking of a pie, how would you split that pie so that everyone around the table receives an equal share? Sort of. So now, in this case, when you're looking for one pole, they say, okay, just take 2 poles and only keep the ones in the left half plane. So now you split your pie in half. I like this pole because then you get half a pie. So now you get 180 degrees, right? Now, if somebody said, oh, give me a 2-pole or a second order Butterworth. Now, if you looked at this one, the first order, you say, oh, I divide 360 by 2, and those poles or singularities are split, or they're 180 degrees apart. Now, you want 2 poles for the next higher order. So that means we look at 360 divided by 4. We double the 2 to get 4. 360 divided by 4 is 90 degrees. And if we have 2 poles in the left half plane and 2 poles in the right half plane, and if I have 2, I can't have a real one, can I? On the on the real axis. So now I have 2 poles in the left, 2 poles in the right, and they have to be 90 degrees apart, all of these poles. So if you were thinking about that, you would say, oh, here's 90 degrees, and over here, here's 90 degrees in terms of separation. And your 4 poles would be, there are the 2 that you would keep, and then these are the 2 that you would throw away. And those are now where you would locate your Butterworth poles if you wanted a second order filter. You would just have that one in the, is that the second quadrant, and the other one in the third quadrant. You want them both in the stable location. Now if you had 3 poles, whoa, now you have 360 divided by 6. Oh, still pretty easy. 60 degrees is your separation. And now you have 3, you have an odd pole. So one of those poles will again be at -1. But what's the separation now between these poles? It's 60 degrees. So now you would go from here up to 60 degrees, and that would be your positive, let's say, complex conjugate pole, and your other one would be down here at -60, and then these 3 over here you would be throwing away anyway. Question? So is this related to quadratics and damping? Somewhat, but not really. So the question was, does this have anything to do with quadratics and what we were talking about before? It does if we stop with the second order. So in Bode plots, when you have a quadratic, that means you have these 2 poles right here. Right? And now if you had to sketch the Bode plot associated with those 2 poles, what we've agreed on between you and I this semester in this class is we're going to simplify things. And the way that we are simplifying things is we are rotating those 2 complex poles down to where they have a damping ratio, a zeta equal to 1, and making both of those real. So we're throwing away the imaginary piece, but we rotate them so that their natural frequency stays the same. They stay exactly the same distance away from the origin. So in a Bode plot, we say, oh, between you and I, let's just quickly sketch this. I'm going to make those have two real poles at a distance of omega sub n into the left half plane. And that's the connection. But if we now wanted to look at a third order polynomial, you would now be looking at, let's say here, if that's 60 degrees and this is minus 60 degrees, and then you have your third pole right there. Those triangles would be your three poles for a third order. If you had a fourth order, now you're dividing 360 by 8, right? Or let's just divide both by 4. Now we're looking at 90 divided by 2. 45 degrees is our angular separation. And if we have 4 poles in the left half plane and 4 in the right, because we have a total of 8, and they're separated by 45 degrees, then I have to be up here 45 divided by 2 and down here 45 by 2, 45 degrees divided by 2, and then I'm 45 away from this one. So my 4 poles would be 2 here and 2 there. Is that making sense? Well, all of this discussion was to try to make you see where the roots of that fourth order are located. So if you took the roots of that, those would be distributed in that left half plane on that unit circle at those angles. And you could calculate with your quadratic formula where those roots are located. That's where they are. I'm not sure why I went into all of that, but maybe you start to see the picture of where these poles are located on the unit circle in a Butterworth filter. And that choice of pole locations makes your magnitude plot maximally flat. Pardon? Even if the two, these two functions are not the same, are they? What are you, I'm sorry, I'm not sure I understand the question. So now if you had a double pole, you're not going to have a double pole in these Butterworth polynomials. So now what we see is we are going to have, if I can come up with a different geometric shape. Did anyone do that? Did anyone find the roots of this one? Where is it? Well, if you just completed the square, you would know that the real part was half of 0.765. So it's at minus 0.35 something, right? Minus 0.38. And it's going to be up. So if I do a different, so the triangles, if this is going to make sense later, whoops. The triangles were a third order. Why don't I do the squares for a fourth order? And I just said that those are now here. And 45 degrees down from that on the top, or this one's now at a real part of minus 0.9 something, isn't it? With an imaginary piece not quite as big. So it's, let's say, right there. If you could sketch better than I could, this distance right here and that distance in angle is 45 degrees. This distance is 45 degrees. This distance is supposed to be 45 degrees. That's for your 4 poles in a Butterworth configuration in the left half plane. Is that what you end up with when you factored those two polynomials? And they are, if you calculated the hypotenuse for each of those squares, that hypotenuse, or the distance they're away from the origin, would be 1. Now, what in the world am I wanting to do? Well, probably you're not going to be designing all of your filters with a bandwidth of 1 radian per second, are you? But that's what this picture is showing, and that's what your table gives you, are these polynomials with a natural frequency of 1. So we have to figure out, how do we rescale those? How do we change those frequencies from 1 to something else? Let's now just agree that this polynomial right now, which was s squared plus 0.765 s plus 1 and s squared plus 1.848 s plus 1, this was a normalized fourth order polynomial. What we want to do, suppose we want a new bandwidth. And if we want a bandwidth bigger than 1, can you see that this circle just gets bigger in radius? We now want our poles to be exactly the same angular relationship to each other. It's just we're going to grow this circle. So if we wanted a bandwidth of 2 radians per second, we would just double the radius and basically find our poles by drawing a ray from the squares to the omega equal 2 circle. All right, so suppose we want a new bandwidth, and let's let our S new equal, for whatever reason, pi over 2 radians per second. And how are S new and S old related? If we used our previous formula, it would be this scaling factor, K sub f, times S old. Now, we just said that S new was pi over 2, which is a little bit bigger than a half, right? Since it's 3.14 divided by 2, that's actually 1.57 in numerical form. And that's now equal to pi over 2 times S old. Now, what we want to do, if we're looking at this normalized fourth order polynomial, that's actually our old S. And we want to create a new polynomial that has a different frequency. This one has a frequency of 1 radian per second. So what we need to do is we now need to rewrite S old in terms of S new. Because we now know up above what S old was. Now we can say, oh, if we just replaced S old everywhere with 2 over pi S new, then we would be in business. So this we now use to replace S in our normalized polynomial expression. Or we now have 2 over pi S squared plus 0.765 times 2 over pi S plus 1. That's the first piece. And that's now times the next polynomial, which is 2 over pi S squared plus 1.848 2 pi over S plus 1. And if you multiply all of that out, you end up with 0.405 S squared plus 0.487 S plus 1 times 0.405 S squared plus 1.176 S plus 1. And that's now your new fourth order polynomial, if somebody needed one, with a cutoff frequency of pi over 2, 1.5, 1.57. So that's how you could rescale if somebody said, oh, give me a Butterworth filter polynomial, a denominator polynomial that has poles such that I have a bandwidth of 27 hertz. Then you could do it using this technique. Questions on that? That's frequency scaling. And I talked about it based on this S-plane picture of where the Butterworth poles are distributed or located in the complex S-plane. Let's then look at these Butterworth filters in terms of how can we build them. And what do we know once we start talking about Butterworth? The reason we're doing that is because we want a flat magnitude spectrum in the passband. If we just kept cascading our first order RC filters together, the first one would bring us down to minus 3 dB at omega equal 1. If we now put another one on, we would be another 3 dB down from that. We would be at minus 6 dB right at the cutoff frequency. So our cutoff frequency really is smaller than 1 if we just kept adding sections together. We don't want that to happen. We want to have a flatter passband magnitude curve than the previous low-pass filters. And the second order section that we are going to use for our Butterworth is we're going to have a resistor and another resistor and then a capacitor going into the op amp. We have negative output feedback, and we're going to put another capacitor there. We'll call that capacitor C1, and these two resistors will be equal, and here's C2, and here's our input V sub I. That's our second order section, and we should be able to derive the transfer function for that particular circuit. You could simply do some KCL equations and find the transfer function, and if we did that for this circuit, our transfer function H of S between the input V sub I and the output V sub O will be 1 over C1 C2 all over S squared plus 2 over C1S plus 1 over C1 C2, and that's with these R's set equal to 1. And if we normalize that to have a bandwidth of 1, what would that force upon us? So this is now a second order low-pass Butterworth filter. If we wanted to normalize that transfer function, that means we want to make that constant equal to 1. If If we wanted to make this have a natural frequency of 1 radian per second, then we would want that constant in the denominator, that 1 over C1, C2, we would want that to equal 1. And that last polynomial, second order polynomial, has a natural frequency of 1. If we now compare that polynomial with the denominator in our transfer function h of s, this now says that 1 over C1, C2 is equal to 1. Or C2 is equal to 1 over C1. And by looking at the coefficient of the S term, we see that B1 should be 2 over C1. So if we can now find B1, then C1 is going to be 2 over B1. And once we have C1, the reciprocal of that is C2. We plug those two values in up here to this second order section, and we now have our second order transfer function with a 1 radian per second bandwidth. Questions on that? So with this technique, now we can go back, and if somebody gives us this fourth order, we can now put two of those second order sections back to back. One of those sections will have a B1 of 0.765. The other one will have a B sub 1 equal to 1.848. And in each of those two sections, you now know what C1 and C2 are, and your R's were all set equal to 1. So now you have the fourth order low pass filter with Butterworth poles with a bandwidth of 1 radian per second. If you don't want a fourth order, you can cascade these together with a first order to get whatever you want. So one can cascade these second order filters or sections. Let me say filter sections. With the earlier first order filter, to produce or to obtain higher order filters. And the higher the order, the closer the magnitude characteristic comes to the ideal magnitude characteristic. And what is the ideal magnitude characteristic? If I said, oh, what's the magnitude in the pass band equal, and what's the magnitude in the stop band? So those are our ideal values. We want a pass band of 1 and a stop band of 0, and the higher our filter order, the sharper the transition between our pass band and our stop band. Let's now look at the formula that we can use to determine what filter order we would like to use. So here is a formula for determining the order of a Butterworth filter. It says that the filter order N is equal to minus 0.05 A sub s over the log base 10 of omega sub s over omega sub p. And that should be very clear. I've put some variables in there that we have not yet defined, right? So now we are assuming, well, I have to first tell you what we're assuming. N better come out, well, N can be some real number, but you're going to have to up it to where it becomes an integer, right? Because you can't design a 1.67 order filter. That would say, oh, I need a second order filter. If N ends up being 2.4, you say, oh, I need at least an N equal 3 filter to achieve my specifications. Let's write down or sketch. Oh, and I should maybe say that this is an approximate formula. It's better when 10 to the minus 0.1 A sub s is much bigger than 1. And A sub s is a value in dB. And this approximation is best or better when A sub s is less than minus 10 dB. Because if A sub s was minus 10, now you have 10 to the minus 0.1 times minus 10, or 10 to the 1, that's when it's equal to 1. So you want A sub s bigger than minus 10 dB. Here's the picture that I'm using in that definition. There's the picture. I'm actually interested in this point that's 3 dB down from the, let's say, the pass band magnitude. And this point in frequency is my pass band frequency, or the cutoff frequency. That's my cutoff frequency in this picture. And then I want to consider how far down I am in dB at this, let's say, stop band frequency, omega sub s. Let's look at an example so that maybe this makes a little bit more sense. But those are the values or the variables in this expression. Here's an example. Suppose that somebody says, oh, I want a cutoff frequency of 2,000 hertz. And I want to be actually 16 dB down from the passband magnitude at a stop frequency of 10,000 hertz. That's the specification. I want to have a 3 dB frequency of 2000, and I want to be down 16 dB by the time I reach 10,000 hertz. That's how steeply I want to fall off or roll off between the pass band and the stop band. So in this case, my cutoff frequency, well, let me just draw a picture. Here's my F sub P, and here, let's say, is my F sub S. And I want this to be at minus 16 dB. And if you wanted to, you could check the approximation, and it ends up being about 40. So 40 is bigger than 1. If you wanted to check to see if this approximation was going to work, you could say, oh, 10 to the minus 0.1 times minus 16 is about 40, and I'm just going to say that that's much bigger than 1. So now we can use our formula, which says, oh, the order of our filter needs to be this minus 0.05 times A sub S, which is in dB, so that's minus 16. And now I take the log base 10 of omega sub S over omega sub P. But it doesn't matter because omega is 2 pi f, so I could put this in terms of frequency of hertz. So I can now say that this is 10,000 over 2,000. All right, now I'm looking at the log of 5, basically, and the log of 5 is what? 0.7, roughly, and now I have 0.8 upstairs, so I have 0.8 divided by 0.7. That's a little bit bigger than 1. But that says then I would need a second order filter to satisfy this specification of being 16 dB down by 10,000 hertz. So I need a second order filter. Questions on that? You have to, well, depending on how close you are to the integer, you might have to go negotiate with your boss or somebody. If you say, oh, 1.14 is close enough to 1 versus me having to build a second order filter, maybe they're okay with that, but you're not going to satisfy your dB spec with a filter of 1. You'll be close. What? So you could approximate what A sub S is using this formula. But again, this is an approximation that assumes that you are at least 10 dB down in your transition between F sub P or omega sub P and omega sub S. How do we put all of these pieces together so that you can now run across the street and ask Josie? She's probably wanting to close down the labs for the semester. But now you can say, Josie, I need to design a low-pass Butterworth filter. And she'll say, okay, what are your design specs? Wow, tough crowd today. Must be trying to finish up the homework assignment. First thing you need to do, and you think I'm not paying attention. First thing we need to do is figure out what's our first step. If we're going to design a low-pass Butterworth filter, what are we going to do? What's our first step? we need to be told sort of what the design specs are, and based on that, the first thing we probably need is the order of our filter, right? Somebody needs to say, or you need to determine based on that previous formula, what's the filter order. So now we know how to determine the filter order, so let's now determine that based on somebody's specifications. We determine the filter order. And we've just shown how to determine that we needed a second order filter. Once we found the filter order, now we can go back to our table of denominator polynomials and find the normalized denominator in, let's say we're still with our textbook, table 15.1 in the textbook. If we now need to design a sixth order filter, we're going to have second order sections. I'm sorry, 3 second order sections in that table. So now we need to combine all of those sections, depending on the order of our filter. We need to combine the second order sections. And that should be figure 1521 with our first order, if we need it. And the only time you will need a first order is when you end up with n being odd. So now if n is odd, you will need to combine or add in a first order section. And that's the very first figure in the book. I'm sorry, in chapter 15, 15.1, to obtain the realization or the physical device that will satisfy your filter order. All you've done now is put all of these different second order sections and maybe a first order section together. And the R's and the C's are yet to be determined, but the R's we've said are 1 for omega equal to 1. What we need to do now is we need to find the capacitor values. So find the capacitor values in each of the second order sections, because each of those will be different, meaning we are going to use this normalized formula, and from that we know that B1 is equal to 2 over C1, and C2 is the reciprocal of C1. That will now give us a 8th order low pass filter with a cutoff frequency of 1 with those choices of R's and C's. The R's are all equal to 1. Now what we need to do is frequency scale. And if you only have certain capacitors that you can use, you may want to magnitude scales. Or if you only have certain resistors that you can use, you may want to also magnitude scale the components that you're using. And finally, if you need to adjust the gain, if somebody said, oh, I need a passband gain of 4, well, the circuit that we've presently built doesn't do anything with the overall gain. It just adjusts the cutoff frequency. but we can introduce or cascade another circuit. So introduce an inverting amplifier circuit. If we do need gain, or if gain is needed. And now hopefully you haven't thrown out the first half of your textbook. That's back in chapter 5, which is apparently a very popular question for interview purposes, is to sketch an op-amp circuit. And you could say, oh, would you like me to draw an inverting amplifier? Then you could simply say, oh, here's my feedback resistor, here's my input resistor between the output terminals and the input terminals. Pardon? And that will be minus this. We now have that for its transfer function. And if we needed to not be having an inversion in our input-output relationship, we could put another inverting amp on that that had a gain of 1, or we could put 2 together that split the difference on our gain, if that was more effective. Questions on that? That's our process. Let's now use that to design a filter. Suppose now that we want a third-order filter. What's the roll-off rate at high frequencies? What's the magnitude slope going to be at high frequencies for a third-order filter? It'll be 20 dB down for every order. So it's going to be 60 dB per decade. If I said, what's the phase shift at high frequencies in this filter? Low pass. What would it be? Minus 270. So we have 3 poles, nothing else. We have a net 3 poles. If I said, okay, what's the phase shift at low frequencies? 0. So that now our input sinusoid or cosine is lined up with our output sinusoid or cosine at low frequencies. Question? So now the question is, if this was in our system, would it matter that our input and output were shifted by a certain amount? What we want to do is we want to preserve the same time shift between all frequencies. So we need a linear phase shift. And you might learn this more in 340. You might not. I don't know. We'll see. I don't know what I'm teaching. So now what we have is, if somebody were interested in the input and output relationship of one frequency, it's probably not going to matter, is it? Because we don't even hear the input. All we hear is the output. And what's the phase shift doing? It's just shifting in time. So if it's a millisecond or 2 delayed, we don't care because we never heard the input. But if your system is trying to process a musical composition and it has all these different frequencies, well, you better hope that your system does a good job with a linear phase shift so that all of the frequency components come out at exactly the same amount of delay. So if one component is delayed 0.6 milliseconds, all the other frequencies better be delayed by that same 0.6 milliseconds. Otherwise, you're going to get a blurring of frequencies in time with each other, and you're going to go, where did that noise come from? That might make more sense studying for the final. Okay? But that's an important point in terms of phase shift and frequency response. That's what we're doing all these Bode plots for. Now you can tell me, if I give you an input signal at a certain frequency, you can say exactly how the magnitude will be adjusted and its phase will be adjusted in a sinusoidal steady state. If we now have a third order filter, what do we know? We can immediately go to table 15.1 and find the denominator polynomial associated with the third order. And that's going to look like a first order factor together with a second order factor. And now what we want to do is we need to build this, or we want to build a filter, a combination of factors that realize these two pieces. The first order piece we will build with figure 15.1 circuit, and the second order piece is our second order section that we've just talked about. If you wanted to know where these poles are in the complex S-plane, you better be able to tell me that at least one of them is somewhere. Where do you know? Are these are normalized, aren't they? All of their coefficients, constant coefficients, are 1. And the polynomials are monic, meaning the coefficient of the highest power of S in each of these pieces is 1. So if you got rid of the damping, this would be an S squared plus 1, and you could say, oh, that would resonate right at plus and minus J1. This one, the first order piece, you could say, oh, if I set that equal to 0, that's at S equal minus 1. So they are on this 1 radian per second distance away from the origin. And you could find the roots of that first one. The real parts are at minus 1/2, and the imaginary parts are such that you get 1 when you find the hypotenuse. And that's going to be the square root of 3/2, I think. So this now, if you factored it, this would have poles at minus 1/2 plus and minus j square root of 3/2. That's where those two are. Okay, and those should be 60 degrees away from the minus 1 pole. In our second order section, now what do we do? Well, now we need, or in this second order section, what is B1? In this second order polynomial, what is B sub 1? It's 1, isn't it? B sub 1 was the coefficient of the S term. And how was B1 and C1, how were those two related? So this was 2 over B1, wasn't it? So C1 is 2, and C sub 2 was the reciprocal of C1, or that's equal to 1/2. Meaning now we know exactly what our normalized filter looks like as far as the second order section is concerned. There's our second order section. We are going to cascade that with this first order section. It's had enough. And those will be the feedback path are what are R values. Then we will have our assignment number. Number 10, it should be coming shortly.